Good morning. I hope you all had a great weekend and a happy Halloween, all that jazz. Today, we're going to start an exam review for the second midterm, but today at 1 o'clock in lab, we're going to talk about chapter 5, all right? So today at 1 o'clock, 1:10 p.m., when you come to class, you'll turn in the Lewis Structures lab that we started last week. Problem set number 5 is up. We'll then take seminar self-quiz 5 first, followed by actual quiz 5, and then we'll go next door and do the valence bond and molecular orbital lab. So again, we're going to start an exam review today, but the exam is actually not until next week, Monday. So next week, Monday, for you in section L1, the midterm will be, which is Monday, which is November the 10th. 1:10 p.m. So we won't do problem set 6 or any of the self-quizzes and stuff next week. We'll do the midterm like we did with the first midterm. Now, when you come to the actual midterm, there will be another exam prep worksheet due. Exam prep 1 was a single page, double-sided. Question was given. Most of the time the answer was given. You show your work how to go from the question to the answer, good to go. And exam worksheet 2 is very, very similar. All right, there's a question followed by the answer, show how you do your work, and you're good. The lab that we start today, valence bond and molecular orbital lab, will be due next week, Monday. The lab next week, Monday, though, is kind of cool. It's called the Empirical Formula Lab, and this is one where you definitely will need some safety goggles, all right? We're going to have flames and vacuums and all kinds of cool stuff. So anyway, color changes, it's quite a spectacular lab. So after the paper labs we've been doing, this will be kind of a cool transition. So bring your safety goggles next week. The format of the midterm is exactly the same as the previous one. There'll be 12 multiple choice questions, four short answer questions. It's about 90 minutes in length. And when I return it to you, there'll be a summary sheet at the end saying how you're doing in the class as of this moment. So it should be a very similar format. Shouldn't be any changes. Questions on this kind of stuff?
Do you know, I guess, is there a place we could go that would have kind of more practice questions for this class in general?
Are you looking for stuff for the midterm or stuff all over chemistry?
Stuff for the midterm, but also just for, more things like the problem set.
Yeah, so there are practice problem sets in addition to the problem sets, and the answers are given at the end. So after you go through the problem set, those would be a cool study resource. Also, some people start with the practice problem sets and then go to the regular problem sets. But yeah, I've got videos and stuff like that. But also, Brian, if you want to branch out, go to the Khan Academy. I mean, they have really cool things too. And sometimes it's nice to see things from another perspective, another instructor's perspective, and that's legit too. If you have access to a chemistry textbook, every other question at the end of the book is usually the answers given. So that would be another thing you could do totally. So yeah, absolutely. The internet is your oyster. Other questions? All right. So what we're going to do, we'll just start some review questions. The first ones will be more aligned with last week's problem sets, and the last ones will be more aligned with the one we're going to do today. So let's check this out. Here are 4 Lewis structures or electron dot structures, and one of them is not correct. See if you can tell which one up there is not a legit Lewis structure. I'll give you a few minutes to think about it, and then we'll talk about what the actual answer is. So. Okay, so on a problem like this, if I see it, the first thing I do is I try to make sure that everything has its octet or it's a happy atom, quote unquote. Most of the time, atoms want to have an octet. Some things can go under. So for example, this hydrogen only has one bond, which is fine. Hydrogen's okay with one bond. And boron, aluminum, gallium, beryllium, they can have under an octet and be fine, but we don't have any of those atoms. And some things can go beyond the octet. So anything in period 3 and lower, so silicon, sulfur, bromine, et cetera, but none of those are this either. So when you look at these, like this nitrogen has 3 bonds and 1 lone pair, so that's an octet. So those all look happy. Carbon here has 3 plus 1, 4 bonds, it's okay. Oxygen has 3 plus 1, 4. Carbon even has 3 plus 1, 4. So that everything on that level is fine. So it's going to be more than that. Now, in the Lewis Structures lab, I told you how carbon usually likes to have 4 bonding pairs and no lone pairs. So that one definitely looks suspicious. So I would start with CO, carbon monoxide, and this will be a good chance just to talk about Lewis structures as well. So when you want to draw a Lewis structure, you count up the valence electrons. Carbon is 4, oxygen is 6. So that's 10 valence electrons. If you divide it by 2, that would be 5 pairs. Connect the outer to the inner atoms, but in this case, there really isn't an outer and inner. You just kind of put them around. This is one of my 5 pairs. Oxygen is more electronegative. I would put the electrons on the oxygen first and then the carbon if there's any. So 1, 2, 3, 4 gives that. That's all the electrons I have. Carbon does not have an octet. It needs to have at least 4 pairs around it. So I would make not just 1, but 2 lone pairs. If you move the lone pair right there, that's what this structure is. And believe it or not, this is the legit structure for carbon monoxide. Carbon in carbon monoxide is one exception to the no lone pairs. Every other thing you ever see is, as far as I know, is different, but this one's not. So that's okay. The next thing I would try is try this NO thing. That looks a little weird. So if you have something like NO minus, same thing, count up electrons. Nitrogen is 5, oxygen is 6. You'll add 1 because it has a -1 charge. 6 plus 6 would be 12 valence electrons or 6 pairs. And maybe now you can see what's going on here. Connecting the nitrogen to the oxygen is 1 pair. I have 5 pairs left. Put them around oxygen first. It's more electronegative. Now I have all of my 6 pairs. Nitrogen has 1, 2, 3 pairs. Like carbon, it needs to have 4. It'll have a double bond, but this structure shows NO with a triple bond. So NO minus is not this structure. NO minus would have a double bond around it, not a triple bond. This structure right here, when you figure out its electrons, is actually NO plus. So these are the kind of things I think about when I figure it out. You can see sometimes it's a little trial and error. We're going to look at some structures like CO and NO in the lab today. So this is kind of cool to show how you would draw a Lewis structure form. But this thing here then would not be NO minus, it would be more like NO plus. Questions on that? Here's another example. You can use the same principles to see what's happening, but this one you can see maybe that there's something wrong about one of the structures right away. So see if you can figure out what's wrong with one of those structures. All right, so again, when you have a question like this, I would look for things which are somehow breaking what they need to make them happy, to have formal charges of 0. And again, like hydrogen's okay with just 1, but all the other period 2 elements, which are nitrogen, oxygen, carbon, they need to have 4. Now, chlorine can go more than 4. It's 3rd period and lower, but on the outside, it will just take the octet. So when you look at this structure, hydrogen's got a bond, carbon's got 4 bonds, oxygen, 2 lone pairs, 2 bonds, happy molecule. Same thing down here, nitrogen has 4 pairs, the oxygens have 2 bonds and 2 lone pairs, except for this one, which has 3 lone pairs and 1 bonding pairs. This is one of the structures from the Lewis Structures lab. This is HNO3 nitric acid. This is okay. This particular thing is weird, but it's all right. Chlorine has an octet. Nitrogen has 4. But what's wrong with this nitrogen right there? Yeah, 5. Good. I see several of you having your hands up. Yeah, it's got 5 bonds. Remember the period 2, which is carbon, nitrogen, oxygen, fluorine, those kind of things, they are limited to 4 pairs. Now, if this would have been phosphorus, no problem. All right, phosphorus is period 3. They're bigger, they can access d orbitals and stuff like that. But little nitrogen can't. So nitrogen and carbon, they're limited to 4 bonds. That structure is not going to fly. So, any questions? Sweet. Okay, formal charges help us to determine what the best structure for lots of molecules are. And I just want to make sure everybody knows how to do it. See if you can figure out the formal charges on the O, the C, and the O, kind of in that order. We'll talk about that a little bit here then in a little bit. So in the lecture section for chapter 4, we talked about why carbon dioxide is best with 2 double bonds to oxygen. If you have a triple and a single, which is a resonance form, you end up with kind of wonky formal charges, not as predictable, blah, blah, blah. So this is where it becomes kind of cool for chemists. You can sometimes predict the best structures and where the reaction will happen on a molecule, stuff like that. There are different ways to calculate formal charge, and I don't care which one you use, okay? But the overall idea is that you calculate formal charge for an individual atom in the molecule, and each lone pair electron counts towards the formal charge. So this oxygen would have 1, 2, 3, 4 lone pairs, and each one of those electrons counts. But the kind of weird part sometimes is that you can either count the number of bonds, or you can take 1/2 the bonding pair electrons. So this line right there represents 2 electrons. So there are 2 electrons in the top line and 2 electrons in the bottom line for 4 bonding electrons total. You can take 1/2 of 4 to get 2, and that's cool. I find it easier to just subtract the number of bonds, which would be 2. And either way you want to do it is great. So for the hydrogen at the top, if you wanted to find its formal charge, it's group number minus lone pair electrons minus number of bonds, or 1/2 bonding electrons. So hydrogen doesn't have any lone pair electrons. It's in group 1. 1 minus 0 lone pair electrons minus 1 bond, or 1/2 of 2, either way. Hydrogen's formal charge will be 0, okay? When you get to this oxygen, it's a little bit more interesting. Oxygen is group 6. There are 1, 2, 3, 4 lone pair electrons, so 6 minus 4, and I would just subtract 2 right there for the bonds. You could also go 1/2 of 4, and either way is fine. But you should find that this oxygen is 0, has a formal charge of 0. Carbon, group number 4, no lone pair electrons, 1, 2, 3, 4 bonds, or 1/2 of 8 if you're doing electrons, 0 as well. And this oxygen right here, group number 6, it has 6 lone pair electrons, so 6 minus 6, minus the 1 bond, minus 1/2 of 2, that one should be minus 1. So when you do all of this, it comes out to be answer D, 0, 0, minus 1. Now, once you've calculated all the formal charges on all the atoms, which includes hydrogen, has to equal the charge on the ion or the molecule if there is one. So this crazy thing has a -1 charge, so something has to be -1. So 0 plus -1, those 3, plus 0 for the hydrogen goes to -1. So this is a legitimate resonance structure. Something has to be minus because of that one right there. If this was a neutral compound, then everything would be 0. You could draw a resonance form with a double bond O right there, and this single bonded electron over there. There'd be a lone pair. You'd get -1, 0, 0, 0. It would still go to -1. Those are both equally cool resonance forms. The more zeros you have, the better, all right? It's the more stealth mode. So when things come in positive and negative and the world is full of them, negative things will see positive charges and positive things will see negative charges. So if we had this molecule and something positive was coming in, I'd say it would attack this negative oxygen right there. So that's another advantage of these crazy things. Any questions? Cool. Okay. Sulfur dichloride is a molecule. It's kind of cool. And what I'd like you to do in this problem is use Vesper geometry to figure out what the molecular shape or molecular geometry of the molecule is. So see if you can use that information to figure out which of those would be the best answer here. All right, so on a problem like this, the first thing, you've got to draw the Lewis structure. All right, SCl2, if you just assumed it might feel like it's linear or who knows what, you've got to kind of see where the electrons are falling around. So valence electrons, sulfur is group 6, chlorine is group 7, there's 2 of them. So 6 plus 14, 20 valence electrons, 10 pairs of electrons. Usually the first atom listed goes in the middle. Chlorine's really electronegative, it won't go in the middle usually. So we'll put sulfur in the middle of the chlorines. We'll connect the outer atoms to the inner atoms. We've got 8 pairs left. Outer atoms first, any left over, put them on the inside. These are all octet-loving atoms. So that's 6 of my 8 pairs that are left. I've got 2 pairs left. 1, 2. And if you step back and look at SCl2 as I've drawn it, your chlorine has 1, 2, 3, 4 pairs octet, good to go. And the sulfur has 1, 2, 3, 4 pairs around it, so it's got the octet. So everything's totally happy about that. Any questions how I got to that part right there? Excellent. Now, the next part is we're using Vesper. And again, Lewis structures are for people like me who can't draw. You don't have to raise your hand if you're one of those people or not. But anyway, I can't draw. So when I draw this, there's no information on geometry whatsoever. Like if you look at just this drawing, it looks like you'd have 180 degrees chlorine, sulfur, chlorine, and maybe 90 degrees to the lone pair. And that's just silly, as we know, because electrons want to be as far apart from each other as they can. So you get better separation if you count up the clouds. Lone pairs and bonding pairs count as clouds. So this is a 4-cloud system. And 4 cloud systems have tetrahedral electron pair geometry. So we're getting closer here. We're looking for molecular shape or molecular geometry, but at least now we know that it's tetrahedral electron pair geometry. So again, my drawing, 90 degrees, 180, totally wrong. It's actually a tetrahedron. You'd have 3 of the 4 of those clouds on the bottom. The sulfur would be kind of on top of the triangle, and then there'd be another cloud on top of the sulfur. Okay, so molecular shape, when you have tetrahedral with 2 bonding pairs on it, is the same as water. All right, water has kind of a V-shaped thing. Chemists call it bent, and that's what we see here for this molecule as well. So bent is the name of the molecular geometry or molecular shape, both ways are fine, when you have 2 lone pairs on a tetrahedral system. Any questions? The punchline is your Lewis structures like mine don't have to have any information, all right? Now, Antonio has better art skills and he draws kind of a CL, SCL, like V. Awesome, that's totally cool, but it's not required, all right? I would embarrass myself if I tried to do it, but a lot of you are better artists than I am, and that would be cool. It's certainly not linear, which is what I drew it looking like. That's okay, Lewis structures don't have any information on geometry. T-shaped is when you have a trigonal bipyramid and 2 lone pairs. That certainly is not what we have. Trigonal pyramid would be the name of a tetrahedron with 1 lone pair, but we have 2 lone pairs, and orthorhombic is something we'll talk about in Chem 222 for solids. It's not appropriate right here. I just threw it in there to mess with you, sorry. Questions? All right, IF2 minus 1 is another molecule. And again, same kind of question. You want to figure out the molecular shape of this molecule, all right? So see if you can, first of all, draw the IF2 minus 1 ion. That's 1 iodine, 2 fluorines, and a minus 1 charge. And then figure out from there which of those would best be represented by the molecular shape or molecular geometry for the molecule. Okay, so just like before, we'll draw the Lewis structure. It's a little weird, but it's nothing you can't handle. IF2 minus 1. So iodine is in group 7, fluorine is also in group 7, and there's 2 of them, and because it has a minus 1 charge, we'll add an electron to it. So that's 7 plus 14, 21 plus 1, 22 valence electrons. That would be 11 pairs of electrons. Now, fluorine, most electronegative, will never be on the inside. I can't think of any exceptions to that. So iodine definitely will be on the outside, and iodine's listed first, so usually it's the first one listed. So we'll put the F's around the iodine. We'll connect the outer atoms to the inner ones. Got 9 pairs left. Outer atoms first, any left over, put them on the inside. So 1, 2, 3 makes that fluorine totally happy. 4, 5, 6 makes that fluorine totally happy. I've used now 6 more pairs. As you can probably see, we've got 3 pairs. So iodine is period 3 and lower. And period 3 is sodium through argon. Anything in that row and lower can have more than 4, all right? And iodine is definitely going to be in that category. Iodine is in group 5. So iodine has extra orbitals to pull upon, all that kind of jazz. Iodine's going to have more than an octet, and that's okay. All right, sometimes iodine does have an octet, but in this case, as you can see, it doesn't. Questions? Okay, now, central atom with 1, 2, 3, 4, 5. What's the name of the electron pair geometry for 5 clouds? Trigonal bipyramid, right on. Thank you for saying it. It's okay. No one has to say it. But yeah, trigonal bipyramid. It's a newer player on the block, all right? Trigonal bipyramid looks kind of like a trigonal planar in the middle. So if you use your imagination, this is trigonal planar, and then there's one on top and one on the bottom. The angles associated with trigonal bipyramid, pretty helpful. 90, 120, and 180. So what we have to do now is we either you know what the name of the molecular geometry is already, or we can think about where to place the atoms. Now, this thing has not just 1 or 2, it has 3 lone pairs. And lone pairs are big and bulky. And they're big, bulky, and negative. So normally what we would do with only 1 lone pair, we try to have as few lone pair atom angles of 90 degrees as possible. But in this case, even more important than that, we need to keep those lone pairs apart from each other as far as you can. So if we put 2 of the lone pairs like above and below, that would keep them apart, but there would be a lone pair in the middle. And that lone pair with both of these would be at 90-degree angles. And that's really, really bad for big, bulky, negative lone pairs. So when you have a molecule like this, you are best, and again, remember that I can't draw, you are best to place the lone pairs in that trigonal planar system, because keeping lone pairs from each other is the biggest thing to think about, all right? So they're going to be all at 120 degrees. That keeps them all at 120. We have no 90-degree interactions. That means then that your fluorines are going to be like on top and on the bottom of that thing. So you're still going to have fluorine lone pair angles of 90, but that is not as bad as a lone pair angle of 90 degrees. So to answer this question, maybe you already know that 3 lone pairs on a trigonal bipyramid is linear. But you can also figure it out, because keeping those lone pairs as far apart from each other as you can is the #1 rule, all right? Lone pairs from atoms is a secondary rule, and that's important too, but it's #1 is keeping those lone pairs as far apart from each other as they can. So this geometry is actually linear. The FIF angle, 180 degrees, which is weird to me. It still kind of blows my way. Blows me away. So anyway, when you're thinking about these structures, all right, just remember keeping the lone pairs as far apart from each other is really important. If we had only 2 lone pairs, all right, there's lots of different things you might do to that. But on the other hand, if you have 3 lone pairs like here, you've got to keep them as far apart from each other as you can. So, questions? Bent is used in both tetrahedral and trigonal planar, and this is kind of a small advertisement for that. Trigonal planar bent is when you have 1 lone pair, and tetrahedral bent is when you have 2 lone pairs, so just FYI on that one. So. Any questions? Polar or non-polar? Think about the structure where we place the fluorines, all right? Do you think that something's going to be pulling opposite, or are they all kind of pulling the same? Non-polar, who thinks it? Polar, who thinks it? Cool. So when you're seeing a molecule like this, if you have atoms that are 180 degrees apart, they will cancel each other out. So I don't think it's too hard to see that the F's are 180 apart. They're going to cancel each other out. So the FIF angle, all of these polarity parts cancel out, no problems there. This one's a little harder to see, but remember, it's like a trigonal planar. And if everything is the same, like we looked at BF3, for example, in lecture, the fluorines pull really hard, but if they're all equal like this one, then it's nonpolar. Well, believe it or not, the lone pairs actually cancel each other out, just like the fluorines do. So this crazy molecule is actually nonpolar. The lone pairs cancel because they're in the middle there, the trigonal planar, and the F's actually cancel each other as well. So even though you wouldn't think this was nonpolar by any means, all the F's cancel out because they're in the plane, all the lone pairs cancel out because they're in the planes. This is kind of a weird molecule, so yeah. Any questions on that? Yeah.
So the trigonal bipyramid is where the kind of triangles get introduced for drawing out the Lewis structure.
You had triangles in trigonal planar with 3 pieces around it, and the name trigonal was also in trigonal pyramid. So, but what the trigonal planar is different about is that you have like a plane that's a trigonal planar, the old one, and then you have like one above and below.
I'm talking about the above and below stuff, where they use the triangle to show that it's kind of popping out, like in the problem set.
I'm seeing a pyramid, like you have like a pyramid on the bottom and a pyramid on the top. A triangle technically would be just 2 dimensions, okay? So
I'm talking about the actual bond. They draw that as a triangle.
Talk to me after class. I honestly am not seeing what you're seeing, Brian. But yeah, trigonal pyramid, it has its own nuances, definitely, and there's different ways to interpret it. You bet, man. So cool. Other questions? Acetylene is a molecule that has a lot of energy inside it. And we talked about one thing or two that makes acetylene kind of weird. I'd like you to tell me what the carbon-carbon-hydrogen bond angle is. Draw the Lewis structure here, all right, and see if you can figure out. Remember, once again, the carbon likes to have 4 pairs around it. See what you can do. Okay, so on this molecule, when you want to draw the Lewis structure, remember hydrogen is always on the outside, and carbon a lot of times will make a bond to itself. So I would start off by kind of putting the carbons in the middle and the hydrogens around the outside, something like that. And definitely count electrons. So carbon is 4, and there's 2 of them. Hydrogen is 1, and there's 2 of them. So 8 plus 2, 10 valence electrons, or 5 pairs. So start off by connecting all the atoms together. Those are 3 of the 5 pairs, so I've got 2 more pairs left. And you can distribute them any way you want. So for example, you could start by putting 2 lone pairs on 1 carbon or 1 lone pair on each carbon. It doesn't matter. At the end of the day, though, that other carbon, everything needs to have an octet. So in this molecule, you're going to have not just a double bond, because now this carbon has 1, 2, 3, 4, but you actually need to make a triple bond in order to make that other carbon have an octet. So this molecule has an HCCH thing. That middle carbon, whichever one you want, has a triple on one side and a single on the other. Triple bonds and double bonds count as one big cloud. So 1 cloud on this side, 1 cloud on that side, far apart as they can. That's going to be linear, and linear would be 180 degrees. So this molecule is literally just a line. Lots of electron density around the carbons, which makes them kind of cool for welding and stuff like that. Any questions? Okay, this will be a good place to stop. I want to talk to Brian about the triangles because I'm still not seeing it, but your instructor is probably dense, I won't lie. Thank you for being here. I'll see you this afternoon. Have a great day.